Mhm.
Okay, we started hocam.
Okay. Hello, everyone. Now I'm going with the Dynamical Systems lecture series. Cool. I'm sorry, I have to share the screen first. Okay.
I let you.
Yeah. Okay. I have to first share the screen. Wait. Report 1 second. Okay. No, I'm sorry. So sorry, 1 second. I have to share screen with. Where is my? Okay. Now you see the screen, I suppose. Yes.
Yes, hocam, we can.
Okay. So I'm going into dynamical systems, and I'll start with nonlinear. Linear dynamical systems on the plane. Today's topic is nonlinear dynamical systems on the plane. Now, recall, last week we did, last lecture, not week, last lecture, we looked at linear systems. And linear systems were of the form dx dt equals a times x, where x is n vector and A is an n cross n matrix. Okay. In particular, this is an n cross n system. It's linear because the right-hand side is linear. In particular, if n is 2, you get dx1 dt, dy x2. So x is just, let me write it, x1, x2, and so on, xn. Sometimes I will write or x equals, say, x, y, z, and so on. Depending on the dimension, I will use x, y, z, or x1, x2, xn, and so on. Okay, so recall, we looked for special solutions, exponential, say, type solutions. And these solutions were of the form x of t equals some e to the lambda t times some v, with some real lambda constant and v fixed vector. And we found that we have such solutions if and only if, one, lambda is an eigenvalue, and that really meant that determinant A minus lambda I was equal to 0. This is linear algebra, and V is, well, let me say, V different from 0 is an eigenvector, corresponding eigenvector, which says that AV is lambda V. Okay, when you put it on, we get that. Now, this in general, if we are lucky, we will get such n, let's say linearly independent, if you know linear algebra, independent or different solutions, and general solution will be general solution is then the following: x of t equals c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2 plus cn e to the lambda n t vn. So this is like ordinary differential equations, a little linear algebra and so on. So the whole point becomes determine eigenvalues, etc., etc. And should I do an example? No, I won't do an example. We did it last week. But to conclude, I'll give a summary. Again, I'll look at the 2 by 2 case. We have this determinant. Let's say A is just the matrix A, B, C, D. So the equation is dx dt equals A. Okay, sorry, I add a page. Dx dt. Okay, let me write this cleanly. Dx dt equals ax plus by, and dy dt equals cx plus dy. Now, eigenvalues satisfy determinant of a minus lambda I, determinant of what? A minus lambda B C D minus lambda, which is A minus lambda times D minus lambda minus BC equals 0. So you have two roots in general. So lambda is lambda 1, lambda 2, and then you determine V1, V2, the kind of, so to speak, eigenvectors. Okay, so we have, so in general, we have two solutions. Now, what we really did was, what we really did after this was something really nice. We kind of changed coordinates, as follows. This was like, let me write the axis. This was, say, okay, so we had the x-axis, the y-axis, and then we had the two vectors, the eigenvectors, v1 and say v2. So we changed new axis. My new axis will be these guys. So I want to write everything in terms of v1, v2. So what I will get is like my new axis will be something like this. You have the v1 axis and the v2 axis. Okay, and my solution is that I know that v1 of t, I have two solutions. Say, call this new axis like, I don't know, x bar and y bar. This is just a kind of linear change of variables. It's like a shift. It's included in linear algebra. And I will get dx bar dt equals lambda 1, dy bar dt equals lambda 2. Because av1 is lambda 1, v1, etc. So in this direction, it's lambda 1. So I get x is c e to the lambda 1 t, and y bar equals c2 e to the lambda 2 t. Now, eliminating t, my trajectories were then, trajectories will be, well, y bar is something like some constant, x to the lambda 2 over lambda 1. So these will be some curves in the xy plane. X bar, y bar plane. So these will be certain curves, and in the xy plane, they are kind of shifted, turned a bit. Okay, so I know all the trajectories. Now, there were cases, I remind this because I will be using these cases where first lambda 1, lambda 2 real, and say lambda 1 equals lambda 2. One case. Then trajectories are x bar, y bar equals c times x bar, because lambda 1 and lambda 2 are the same. So basically, what sort of picture do I get? The picture I get is something like this. These are the trajectories, are half lines. These are trajectories. And what sort of trajectories are these? These are half lines, because x is c e to the lambda t, y is c e to the lambda t. Now, if lambda is positive, xt starts from minus infinity, no, starts from xt goes from 0 to infinity, and yt goes from 0 to infinity, depending on whether lambda is positive, because x is increasing, lambda positive, x increases. So basically, the trajectories for lambda positive are half lines like this, going from 0 to infinity. Okay? Now, if lambda, this is lambda positive. If lambda is negative, it would be the other way around. The trajectories would be half lines going in. We did this last time. I'm repeating this because I will need things like that. Lambda 2 and negative. Now, if lambda 1 is different from lambda 2, but both positive, then what we get is y equals x to some positive power. Y equals x to both positive or both negative, x to some positive power. So we get curves like that. That's we did it last time, I'm sorry, not last week. So I'm kind of skimming it down a bit. Okay, and the curves will be something like this. These are the curves. Y equals, say, x squared, y equals 2x squared, and so on. Again, starting from the origin, and they go up if lambdas are positive, and they go back if lambdas are negative. They approach 0 if lambda is positive, and they get away from 0 if lambda is negative. And of course, 0 is a fixed point because 0 doesn't really move. If you start at 0, you never go back. So the third case was lambda 1, lambda 2 have opposite signs. Then I get y equals x to some negative power. So if you want to look at the pictures, this is x, this is y. It's a negative power, so basically you have, it's like 1 over x squared, 1 over x, and so on. So you have things like this, and either the arrows point like that, or the other way around. No, I'm sorry, like, okay, I should be careful about the arrows. So let me erase this, and I won't put the arrows, but you have to, depending on which one is positive, which one is negative, the curves will point right or left. And then this is the fixed point, and then you have this special solution if one of them is 0. Of course, don't forget these were eigenvalues, so this is in this x bar, y bar. So this is x bar, and this is y bar. So the picture is shifted and distorted, but these are the pictures you get. Now, why did I do all of these? Because I wanted to remind you of something. And so, okay, final case, let me say final case. If lambda 1, lambda 2 are a plus or minus ib complex valued, then what we would get is, I'm not going through the linear algebra, some linear algebra will bring it down to something like this. Solutions of the form C e to the at sine bt, C e to the at cosine bt. So this is, let's say, again, x bar and y bar. I don't really know what it is, x bar, y bar. And if you look at x bar squared plus y bar squared, what you really get is now sine square plus cosine square is 1. So basically x bar, y bar go around the circle. So x bar, y bar rotate around the origin on a circle or ellipse of radius e to the at. So a is positive means radius goes to infinity. A is negative means radius goes down to 0. So what you really have is kind of helixes, spirals like this. This is A is negative. And then A positive would be the opposite. So here the circles get larger. A positive. You go around circles, and this is some linear algebra. I don't want to elaborate more on this. Now, special case is when A equals 0. So you get x, y solutions are of the form sine t, sine bt, cos bt. So these are circles / ellipses, depending on the radius of thing. So the picture, it becomes like that. And this is the origin is a fixed point. The origin is a fixed point in all of them. Okay, so this was the summary of what I did. Of course, there are other cases, repeated eigenvalues, not enough eigenvectors, etc., etc. There's more linear algebra in it, but this is the summary. Now, okay, I want to recall we had another definition. 0, 0 is a fixed point. So this is called a stable stationary solution because x is 0, y is 0 is a solution because dx dt dy dt equals, well, this matrix is times a times 0, 0, and everything is 0. Okay, axy. So the right-hand side is 0, 0. So that's both are 0. Now, it's a fixed point. Now, we call this point an attractor if, as t goes to infinity, other solutions approach 0, 0. And we call it a repeller if, as t goes to infinity, so solutions get away from 0, 0. So attractor means solutions are going to 0, 0. Repeller means solutions are getting away from 0, 0. Now, if I look at these pictures, let me kind of come back and look at the pictures. I have these pictures. I had the trajectories, remember? And remember, in all these cases, I had these things. If lambda was positive, solutions were moving away, e to the lambda t. And if lambda is negative, solutions were moving towards the center. Same thing if when I had complex roots, I had e to the at. Again, if a is positive, they move away. If a is negative, they come close. So conclusion from last time we said it, conclusion, if both eigenvalues are negative or have negative real parts, then 0, 0 is an attractor. Why? Because as t goes to infinity, e to the lambda t goes to 0. Lambda is negative. Okay, e to the minus something goes to 0. Okay, so the picture is like that. Now, if both eigenvalues are positive or have positive real parts, then 0, 0 is a repeller. So what does it mean? E to the lambda t goes to infinity as t goes to infinity because a is positive. Okay? So the third case, if lambda 1, 2 are pure imaginary, we talked about that. Solutions are circles / ellipses. So the picture was like this: 1 circle, 2 circle, 3 circles, and this is, and we call it 0, 0 is a center. Okay? And 4, if lambda 1, lambda 2 have opposite signs, then we get a saddle point. Then 0, 0 is a saddle point. Remember, the picture was like this, coming like this. So coming in one direction, going in the other direction, and so on. Whereas like this, like that, etc. So it's really like a 0, 0 is a strange structure. Okay, if the eigenvalues are of different or of opposite sign. Okay, this was the summary of what we did sometime. Now, more complicated cases, what if lambda is 0? I didn't say that. I don't want that case, so I'm not going to mention it. And it's not like an edge case. Okay, so enough of linear. Now, what about nonlinear? Nonlinear systems. Okay, I'll start with an example. I have prepared a few things here. Okay. Okay. dx dt equals x squared y cubed, and then dy dt equals x cubed y squared. This is my nonlinear system. Okay, now it's not easy to solve, but the trick was eliminate t. So t doesn't really go anywhere, and write dy dx is dy dt divided by dx dt. That's chain rule. So this is x cubed y squared divided by x squared y cubed. And then when you do the simplification, you get dy y dy equals x dx. And when you integrate it, you get y squared over 2 equals x squared over 2 plus c. And then you get trajectories are the curves y squared minus x squared equals constant. These are the trajectories. You get these trajectories. Now, again, sketching them is not very difficult. How do I sketch them? These are like hyperbolas. These guys are hyperbolas, or lines, y, x equals plus minus y. So we have the two lines here, and then we have the other hyperbolas here. Okay, and of course, 0, 0 is the only is the fixed point. So that means 0, 0 is a stationary solution. Why? Because if you put x equals 0, y equals 0 is a stationary solution. So I have a stationary solution here that doesn't really move. And I have the other solutions. And which way do they go? Well, I don't really know, hyperbolas. But if you look at the signs, you'll say these are like all the trajectories. Okay. But now, unfortunately, I have to add a few pages, sorry. But now, unfortunately, this trick does not always work. So in general, I have dx dt equals f of xy, dy dt equals g of xy. That would give me, the trick is dy dx equals, what is it, gxy over fxy. Is usually too complicated to solve. Okay. This is usually too complicated to solve, so this is not a good way to approach the thing. Now, what we can really do then is the following. First of all, we will kind of some definition. We say that a point P0, which is x0, y0, is a stationary point solution or a fixed point of the system, nonlinear system, if the following holds: f of x0, y0 equals g of x0, y0 equals 0. Okay, so this we call a stationary solution. Example, let me give an example. Say, look at this, dx dt equals, I have one example here, I want to write that down, e to the x plus y minus y, dy dt equals minus x plus xy. Now, this is kind of a strange system. Now, what is the stationary, what is the fixed point? If I want to find the fixed point, okay, let me find the fixed point of this. I'm looking at the fixed point. Means I have to solve e to the xy minus y equals to 0 and minus x plus xy equal to 0. Now the second one gives me x times y minus 1 equal to 0, which gives me x equals 0 or y equals 1. Now if I come back here, if x equals 0, then I want to say e to the y minus y is 0, but e to the y is always bigger than y, always. So it doesn't work. If y equals 1, then I get e to the x plus 1 equals 1. So that gives x plus 1 equals 0, so x equals negative 1. So one fixed point one fixed point, P0 equals minus 1, 1. Indeed, when you plug it in, and so x is minus 1, y is 1 is a solution. So basically, if I look at my graph, my good graph, I have this, right? And I have this point, 1 minus 1 over here. This is my fixed point. So I have a solution like this. Now, my question is, how will solutions look like near P0? This is an easier question. Instead of saying, how are all the solutions? I'm just trying to wonder how the solutions are in like P0. In other words, that is, if I zoom, so if I zoom near P0, how will the trajectories look? So I'm basically trying to zoom around here and see what happens around here. I don't really care what happens far because it's too much complicated, but I really want to see this is what happens here. So this is my region of interest, so to speak. I want to see what happens on this side. Okay, for that, remember we had, again, calculus helps us. The trick is linearization. Yes, linearization. So if I have a function f which is differentiable, then this tangent line, well, it's not really tangent line, but the tangent approximation tells me that f of x, y is approximately equal to f of x0, y0 plus f sub x at x0, y0, x minus x0 plus f sub y at x0, y0, y minus y0. This is the tangent space approximation, tangent plane approximation. And this is a good approximation if xy is close to x0, y0. Okay. Now, okay, so now note if P0, x0, y0 is a fixed point, then fp0 and gp0 are 0. So that means f of xy will be approximately f sub x a times x minus x0 plus p times y minus y0, and g will be approximately c times x minus x0 plus d times y minus y0, where what is a, b, c, d? These are the partial derivatives f sub x, f sub y, g sub x, g sub y at the point P0. So this is the approximation we know. Now let's apply to our case. Apply to our problem. What was our problem? Here we had f was equal to e to the x plus y minus y, and g was equal to minus x plus xy. I think, correct? Yes. Then f sub x is, and the point P0 was minus 1, 1. So f sub x is e to the x plus y. F sub y is e to the x plus y minus 1. G sub x is minus 1 plus y. And g sub y is x. So at P0, this matrix A, which is A, B, C, D, is what? You put e to the 0, which is 1. E to the 0 minus 1 is 0. Minus 1 plus 1 is 0. And g of y is x is minus 1. Okay, that's 0, we get this. Is that good? Yes. So the vector fxy, gxy, is approximately what? 1, 0, 0, minus 1 times x minus x0, y minus y0. So this is basically x minus x0 times, well, let me stop here. Let me kind of, okay. So how do I conclude this? So my system is then my system becomes approximately dx dt equals 1, 0, 0, minus 1. X minus x0 was, now what was x0? Remember x0 was minus 1 and y0 was plus 1. So it's x plus 1, y minus 1. Okay, so this is approximately that. Now, this is not a linear system, because a linear system should be axy. It's not, right-hand side is not axy. But if I change variables, this is a trick we do all the time. What do we get? We get to x bar equals x plus 1 and y bar equals y plus 1, no, y minus 1. I get, I'm sorry, dxy dt, d dt of x bar y bar equals minus 1, 0, 0, no, plus 1, 0, 0, minus 1 of x bar y bar. Or if I write it properly, I get, okay, let's see. So this is a linear system. Linear system. What about the eigenvalues? So I have to look at determinant A minus lambda I, which is determinant 1 minus lambda 0, 0, minus. I'm sorry, did I do it correctly? Okay. So I'll get A minus 1. Okay, minus 1 minus lambda. That's equal to 1 minus lambda times minus 1 minus lambda. So that gives lambda square minus 1. So that gives lambda equals plus minus 1, two eigenvalues. In fact, we don't really need that much. The equations become, I have dx bar dt equals x bar, and dy bar dt equals minus y bar, which, remember, this was giving me, what was this giving me? This was giving me, if you want, let's put it this way, x bar equals c e to the c1 e to the t, and y bar equals c2 e to the minus t. So this would give x bar y bar equals constant. So the pictures are, let's see, in the xy plane. So this is my X bar, Y bar plane. How are they? They are X bar, Y bar equals constant. These are hyperbolas like this. And then you have 0 as the center, and you have these lines. Now, how are the arrows? You see, X bar goes to infinity, and Y bar goes to 0 as t goes to infinity. So X bar goes to infinity, but Y bar goes to 0. X goes to infinity, Y bar goes to 0. Okay, this is the picture. Now recall that X bar was X minus 1 and Y bar was, no, was it X plus 1? Let's see, what was X bar? Okay, X bar was X plus 1 and Y bar was Y minus 1. So if you kind of look at the real picture, how is the real picture? Let's sketch the real picture. Okay. So this is X and Y. Now the fixed point is here, minus 1, 1. This is the fixed point. These are the two fixed axes. And the hyperbolas are like this. Okay. But this is solution of the approximate system. And then you would expect that the solution of the system should look like that. So we would expect, so let me get this picture. Let me copy this picture. And let's go to the new page. So this is the solution of the approximate system. So if you want the solution of the real system, should be close to that. This is the fixed point 0, 1, and should really be close to that only this is the point, say. This is the fixed point and should really be only approximately equal in this closed region. So basically, we would probably have things like this. You see, I'm distorting the system, but it should be something like this. But only approximation works only nearby. Not approximation works only near the point P0, which is 1 minus 1. Okay? But this really gives us a good thing. Now, but if you look at it, looking closely, we can say that P0 is a saddle, even for the nonlinear system. Okay, because you see, it has all the characteristics of the saddle. It's kind of, these two pictures are similar. One is a distortion of the other. So it's like, I don't know, looking to a kind of mirror that is not perfect. But only locally. Of course, far away, I know that far away, this guy is kind of like that, like this, like that, like this. But far away, we have no idea. Far away, anything can happen. Thing can happen far away, far from this point P0. Because the approximation is only works near P0. Okay, so shall we take a little break and go on? Maybe or just conclude in a while, or
As usual, John. I think.
Okay. Well, maybe we take a little break. I take a little breath, and then
Okay.
in 5 minutes is okay?
Fine, I guess.
Okay, in 5 minutes, we'll go on, and then we'll kind of reach a quick conclusion about what happens in general. Okay?
Okay.
Okay,
Okay.
and bye-bye. Okay, so I stop here. And stop share for the time being. Okay, shall we start again?
Yes, hocam, we can.
Tamam. Okay, so I'm sharing the screen and starting again.
Okay.
I hope I don't have to make it long, but I want to just make a few final points and then get some conclusion, maybe having one example or not. Okay, so okay, so again we have again we have the system dx dt equals f of xy and dy dt equals g of xy, and suppose and p0 equals x0 y0 is an isolated fixed point. Okay, here isolated means there's other fixed points, if any, are not are separated. So basically, like the fixed points would be in the plane, something like this. Okay, so this is one fixed point, this is another fixed point, P0, P1, P2, etc. These are fixed points, isolated fixed points. Isolated means they are really not stuck to one another. If they were on top of one another, they would not be isolated. Okay. Now, okay, a definition. A fixed point x0, y0 is said to be asymptotically, or let's say stable, if any solution x of t, y of t, that is at some point, some time near x0, y0, always stays near. So that means does not get far. So for instance, this is the P0, and a solution that's like this. No, I'm sorry, let me do this as P0. And if my solution is kind of like that, no, it cannot cross itself, so let me be better. This, if it's going like this is like P0 is stable. Unstable means if something like this happens, P0, and if there's a solution that moves far, this is unstable. There's another one, P0 is asymptotically stable. Stable if any solution which starts near P0 tends to P0 as t goes to infinity. So asymptotic stable is something as this is like P0, and you have a solution like this. This is x of t, and then x of t has to approach P0. T moves like this. Okay, so two complex, asymptotic, and then unstable, of course, if it's not stable one way or the other. Now, there is a theorem which says that if near fixed point P0 is asymptotically stable. Actually, let me write it like this. Suppose P0 is a fixed point of the system. Now, if P0 is an attractor of the linearized system, then P0 is also asymptotically stable for the nonlinear system. So the behavior is similar. So what does it really mean? What was attractor? Attractor meant all the solutions approach there. And then note that this happens if all eigenvalues are positive, no, negative, or have negative real part. Okay, this happens if all the eigenvalues are negative or have negative real parts. Okay, because what did we say? If we come back earlier, we said that approximation works, and the solution of the approximate system, remember earlier, is close to the solution of the real system. So if the approximate system is an attractor, that means as time goes to infinity, points gets close, then the approximate system will also be an attractor. We call it attractor or asymptotically stable. Everything gets really close. Now let's kind of go back to the very beginning to see how this thing worked. Remember, as we kind of had all these different pictures, and all these different pictures added up to, if both eigenvalues are positive, the origin, which is like the only fixed point, is a repeller. The solutions move away. Whereas if they are negative, if they are negative or have negative real parts, then 0, 0 is an attractor, which really means, when you translate it, that 0, 0, which corresponds to the, because we shifted coordinates to, corresponds to the system, is attractor. Okay. So this is really important because this allows us, this theorem allows us to classify the types of fixed points and solutions near fixed points. Okay, the solutions near fixed points. Now, why is that? Because, and the reason for the theorem, why the theorem holds, is that approximate systems have approximate systems have solutions that are close to one another. So if the linear system behaves in a certain way, the nonlinear system will behave similarly. So linear system, right, system behaves in a certain way, and then this says that the nonlinear system behaves similarly. Well, let me make a picture or two, and you'll see how that works. For instance, if for the linear system solutions are like this, solutions of the linear system, if the solutions of the linearized system are like that, then solutions of the nonlinear system should be close, so basically should do similar things. They cannot totally go in the opposite direction. These two are close, so stability, so attractor becomes the same as asymptotically stable, etc. And so on. Okay. Depending on how the linearized system works, the nonlinear system works. But there is one exception to this, and let me just do that to conclude. Exception. If P0 is a center of the linearized system, the nonlinear system may behave differently. And I'll give the picture reason. Center, remember what was center? Center was that the trajectories were circles or ellipses. So this is my, say, P0 of the linearized system, and the trajectories are circles. So these are the trajectories. Okay, let me make good pictures. Okay, actually, okay, let's say, okay, let me just look here. One is enough. This is the trajectory of the linearized system. Now, trajectory of the nonlinear system should be close. But what does it mean? Okay, let's put the t here. Say t is going like that. It's kind of trajectory of the linear, so this is periodic and is going counterclockwise. Okay, let's look at the trajectory. So it's kind of like, should be close, but should be close could be, this is close, but approaches P0, but also this is close, but moves away from. You see, stay close does not really tell you close inside, close outside, close getting closer, close not getting closer, and so on. And there's a very standard example. I'll just do that. Okay, maybe I will more or less conclude there because, okay, there's a standard, this is the classical example. And that is this, dx dt equals y plus a times x squared plus, no, a times, one second, let me just not write the wrong thing. Okay. Y times a times x squared plus y squared, and then dy dt equals minus x plus ay x squared plus y squared. A is 1 plus 1 or a is minus 1, two cases. Okay, first of all, what is the linearization? Now, fixed point is 0, 0. That's easy to see. And there's nothing else nearby because the other factors are not 0. But there's a fixed point at 0, 0. Let's see what happens at it. Now, linearization, this is like a polynomial. So dx dt equals y, and dy dt equals minus x. Because when you think of the Taylor's approximation and so, it's like, it's really the first order approximation. These are higher order terms and they disappear. Okay, so the matrix A is 0, 1, minus 1, 0. So A minus lambda I determinant is determinant lambda 1 minus 1 lambda, and this is lambda squared plus 1 equals 0 gives lambda equals plus or minus I. Remember, these were the circles. Real part is 0, imaginary part is 1. In fact, let's see that. Let us see that closer. This closer. Closer. Since dx dt, let's look at dy dx. This was dx dt, no, dy dt divided by dx dt, and dy dt is minus x over y. So this gives y dy equals minus x dx, which gives y squared over 2 equals negative x squared over 2 plus c, which gives trajectories are circles. Square plus y squared equals c. In fact, an alternative way is change variables to x of t equals r of t times sine theta of t, and y of t equals r of t times cosine theta of t. So these are polar variables, polar coordinates. Let's change variables from x, y into polar coordinates. And then it's not, what is dx dt? Dx dt would be dr, well, let me write it as r prime of t times sine theta plus r times cosine theta times theta prime, and dy dt would be r prime cos theta plus minus r sine theta theta prime. Now, if you plug these in and solve, you will get solve for r prime theta prime. you get, I don't want r prime equals 1, theta prime equals 1, r prime equals 0, theta 1 equals 1, which gives r of t equals r0 and theta of t equals t. And that indeed gives circles. So x of t, y of t, x of t is sine t, and y of t equals cosine t. Okay, we get the circles. And r is 1. 1 times sine t, 1 times cosine t. Okay, plus constant, but doesn't really matter. We get circles. And then we have, no, I'm sorry, r0 times. We have the circles here. r0 times, r0 times. Okay, now, what about the nonlinear system? What was the nonlinear system? dx dt equals y plus a times x squared plus y squared, and then dy dt was minus x plus a times y, x squared plus y squared. Now the trick is put r of t as little r of t square, that is x squared plus y squared. Then dr dt equals 2x dx dt plus 2y dy dt. And that is replace them. So you get 2x times y plus ax, x squared plus y squared, plus 2y times negative x plus ay, x squared plus y squared. And what you really get is dr dt equals, now these terms cancel. So you get a times 2a times x squared plus y squared, x squared here, y squared here, times x squared plus y squared. So dr dt equals, you get 2a times r squared. Get this. And r is the kind of radius in polar coordinates. Now, if a is positive, then dr dt is positive, which means r is increasing. If a is negative, then dr dt is negative, which means r is decreasing. But what is r? R is the distance from the origin. So if you look at the solutions, how do the solutions look like? Let me just finish the graph. And so I'm doing two graphs, no, a positive and a negative. Now here, okay, what is happening? We have, again, remember the standard this was the approximate solution. Okay. No, I'm sorry. What was it? Yeah. Okay. Now remember, this is the approximate solution. This was the approximate solution. Approximate solution of the linear system, and this is the approximate solution. The real solution should be close to that. But what is happening? R is increasing, so it's kind of moving away from it. So helix moving away from origin. And again, in this case, this was the standard solution, but here R is decreasing. R decreasing says helix moving towards the origin. So the picture is like this. Okay. So you see the circle case is not really included. Now, I'm going to stop here because I think that's enough for the time being. And this last example that we did with R can be generalized. Let me just write that down. In this last example, we used the function R, which is x squared plus y squared, to in fact show that when A is negative, the system is the fixed point 0, 0 is asymptotically stable. And when A is positive, the fixed point is not asymptotically stable. We use this fact to prove that. Now, this idea can be generalized to what is called the Lyapunov function. So this is like a function V that almost looks like my function R and has certain properties that say that test for stability. This provides a state test for stability. Okay. So maybe next time we will talk about this. But if nothing else, if you just see this, I think as it is, you have a lot of background to understand at least what the main ideas are. So if you read some examples, these words will be familiar, and then you'll be able to kind of work them out. Okay? But anyway, we'll go on with that, but I think this is like a good starting point. Yeah. So I will stop here, I think. Any questions or? Okay. So I'll stop here and then we will meet in 2 weeks after the Bayram. Have a good Bayram.
Thank you, Hocam.
Thank you.